Hello there, and a good welcome to you. This short video is all about free responses that involve the fundamental theorem of calculus. And this will be really quick. I'm just going to run through an example of free response where you might have to apply the fundamental theorem of calculus. But before we do that, let's review some of the basic information about derivatives and their graphical features that the derivative uses to describe the regular function. So a function is increasing if f prime is positive, and a function is decreasing if f prime is negative. Has a relative maximum if f prime changes from positive to negative, and a relative minimum if the derivative changes from negative to positive. All right, so this is all from an earlier unit when we talked about changes into the derivative signs, and we're all looking at whether the derivative is positive or negative, etc. As far as the second derivative goes, a function is concave up if f prime is increasing, in other words, if the second derivative is positive, and a function is concave down if f prime is decreasing or the second derivative is negative. A function has a point of inflection if f prime goes from increasing to decreasing. Oftentimes we'll call that a relative maximum of f prime, or if f prime goes from decreasing to increasing. Right, that would be a relative minimum for f prime. If we need to check absolute extrema, those will only occur at relative extrema or endpoints. Right, so the critical points are what's going on and what we need to test here. So we would test the y values at only those points. Whew, that's a lot of review. So let's apply this review. The first part of the fundamental theorem of calculus made an important connection between the derivative and the integral, particularly what's called the accumulation function. And we would say the derivative with respect to x of the integral from a to x of f of t dt equals f of x. In other words, the derivative of an integral gets us back to an original function. And this is a whole previous video, so if you need to go back and look, I've got another one posted on my website. So suppose that g of x is equal to the integral from 0 to x of f of t dt for the graph of little f below. So this is the graph right here of little f. Not of g. G is the accumulation of the area underneath f. The graph of f consists of two line segments and two semicircles. First of all, what you should write on your paper all the time, whenever you see this accumulation integral, you should write the derivative of g. And g prime is equal to f of x by FTC. Just like so many of the other things we've done with theorems before, this should be an automatic thing that you learn, because it'll be the justification for so many things that you'll write in a problem like this. G double prime of x is equal to f prime of x by FTC, so we might need something about the second derivative as well. What's the value of g of 2? Well, g of 2 is just the area of the triangle that's formed between the function f and the x-axis, going from 0 to 2 with a height of 3. And you'll notice that that's just a triangle, all right? And then when you calculate it, that triangle has an area of 3, all right? Height of 3, base of 2, area of 3. Use the fundamental theorem to explain why the value of g prime of 2 is equal to 3. Well, here's where that thing in part A comes in handy. We know g prime of 2 is equal to f of 2, which is equal to 3. So it's whatever the height is of f at 3, that's the derivative value for g. So in other words, the rate of change of accumulation of area is taking place at a rate of 3 units per whatever. We don't know what the units are. If we have a relative maximum for a function, what do we know happens to its derivative? Well, in a relative maximum, the derivative goes from positive to negative. So why would g of x have a relative maximum at x equal to 5? Well, because g prime, or f, which is this graph right here, goes from positive to negative at x is equal to 5. Again, that's FTC. G therefore has a relative maximum at x is equal to 5. If we know we have a point of inflection for a function, what do we know happens to its derivative? All right, well, the derivative is going to have a relative maximum or a minimum value. Even if the derivative of the derivative doesn't even exist, like at 2 and 3, there's still a point where the derivative changes from increasing to decreasing at 2, and then decreasing to increasing at 3. And then at 5, got all kinds of weird stuff going on. All right, so at these points, x is equal to 2, 3, 4, and 6, we know that g prime has either a relative maximum at x is equal to 2 and x is equal to 4, or a relative minimum at x is equal to 3 and x is equal to 6. And yes, you do need to specify what's happening at each of these points. All right, we can group them together. We can say the derivative goes from increasing to decreasing at 2 and at 4. That's fine. All right, but don't mix up and say vice versa, and that's not going to work because you need to make sure that you're clear with your explanations. All right, explain why we only have to test x equals 0, x equals 5, and x is equal to 7 to find the absolute maximum of g of x. Find g of 0, g of 5, and g of 7, and determine the absolute maximum value of g on the interval 0 to 7. So 0 and 7 are the endpoints of the interval that we have for this function. All right, so these are the only points we need to test, along with 5. Now, you might say, well, what about 3? What's going on with that? Well, something can only be an absolute maximum if it's an endpoint or a relative maximum. It's not going to be something if there's no change in the function at all. All right, if it's just the derivative is 0 and there's no change, then we don't have any sort of maximum value. And then it's also not going to be true if there's a relative minimum value at a point. So really we only need to test 5 because at 5 we have a relative maximum as we discovered earlier. So g of 0, how do we find that? Well, that's the integral from 0 to 0 of f of t dt, right? That's one of our identities of integrals, so that is just equal to 0. There's no area that's accumulated. G of 5, on the other hand, we need to do a little bit of work for. So it's the area of this triangle with a base of 3 and a height of 3. So this area of the triangle is 9 halves. And then the area of this little semicircle right here, which is going to be half a circle with radius 1. So that would be pi over 2 as its area. So overall, g of 5 is equal to 9 plus pi over 2. G of 7 is equal to 9 halves only, and that's because the areas of each of these semicircles will cancel out. So always be looking for some symmetry. It'll make these problems go a lot faster. So therefore, the absolute maximum is 9 plus pi over 2, which occurs at x is equal to 5. All right, so in summary, if you love the previous unit with derivative graphs, you're going to love these types of FTC free response questions. Hopefully we get some practice in class. And just make sure that you always write that g prime of x is equal to f of x by FTC, or maybe you need to write g prime, double prime of x equals f prime of x by FTC, as long as g of x is defined as this accumulation integral, the integral from 0 to x of f of t dt. Thanks for listening. We'll see you on the next video.